All right, let's see. Getting closer for group. Let's see, I'm gonna try to share the window for the screen. Okay, here we go. I think we're good to go. Well, this is Friday, February the 12th. And for Gen Chem 2, finishing our second week of classes with these not so brilliant lectures. Okay, go. All right, so for the announcements. All right, so some of you that are watching this are in my online class. Most of you, I hope all of you in my online class are watching this at some stage, at some point, but also for my in face-to-face class, for my in-class group. Some of you are watching this as well. There was a misalignment of ALEKS dates. Hang on a second. So what happened was when I imported one class into another, it changed all of the ALEKS due dates by one day. So I've gone back and I think everything is synchronized now. So ALEKS 14A, the first part of the kinetics chapter, is due Saturday night. I didn't look up when 14B is due. Let's see. I do have it here. Let's see. Saturday night, the 13th. Yes, so part B is due the 18th. So this is due the night, Thursday night. This is due next Thursday night for 14B. Okay, so next lab next week is kinetics. So I guess I didn't update that. And don't forget that the first exam is either February 18 or February 19, depending upon which class you're in. A couple of pre-med announcements. Ross University, 6 p.m., February 17th. There will be flyers around school. Make sure you take a look at that if you're interested in talking to somebody, some representative from Ross University. And then there's a Pi Night coming up on March the 3rd. Now for Despair, we have something special for you today. This is the Valentine's Day edition of Despair. Love is in the air, and it's pooping on my head. You are special. If you require additional information, get a puppy. The rest of us are trying to work. My reality isn't getting any better, but my fantasies are improving all the time. Money can't buy you love, but it can buy exotic cars and luxury yachts. Once you've got those covered, you'll be fighting love off with a stick. It's over, man. Let her go. And finally, this is harsh. The only consistent feature of all your dissatisfying relationships is you. All right, now that we're duly motivated or demotivated, let's talk a little bit about rate laws. So this is the problem that we ended with on Wednesday, the experimental determination of a rate law. So I believe I went through this, but just one more time, let's talk about this. So the rate this is how you start every rate law. Rate equals K, and then it's always going to be concentrations raised to some power. Remember that M and N are not necessarily the coefficients from the balanced reaction. So this is H2O2, this is I minus. Remember that this little I simply means the initial concentration. Now, what you want to do is you want to keep everything the same. You want to look for two experiments to compare where everything is the same except for one thing that changes. So here, H2O2 stays the same. This doubles. As this doubles, this doubles. So if this is doubling, the rate is doubling, these two are proportional to each other. That means that n is 1. This stays the same between the two runs, and we know that rate is directly correlated to iodide minus, I minus. Let's look at experiments 1 and 3. Here, iodide stays the same, and the concentration of hydrogen peroxide doubles. As this doubles, the rate doubles here as well, from 0.000115 to the 230, 0.000230. So these two are directly related to each other. And as a result, we write our rate law, which is this. Now we know what our exponents are. Once we know the exponents, 1 and 1, those exponents are the same for this reaction, the reaction between these two things, and we don't even know what the reaction is. All we know is that these two are the reactants that combine with each other. Once we have the exponents, the order of the reaction in terms of each component figured out, those numbers stay the same forever. Doesn't matter what the temperature is, these numbers stay the same. These are inherent to the reaction now. If the temperature changes, we know the rate can change. Well, that's the rate constant that changes with temperature. It's not these exponents. Once we have these figured out, they're fixed for good for this reaction. All right, so now find the rate when H2O2 is equal to 0.3 and 0.400. Oh, we need to find K. So we can pick any reaction, any set of experimental data and solve for K. So let's pick number 4. We know that the rate is this. We know that the concentration of H2O2 is this. Concentration of I minus is this. The only thing we don't know is K. And we could pick any of these 4 to solve for K. K better be the same for each of those calculations. So I'm just going to put the numbers in. 0.000460 is equal to, let's see, K times 0.200 to the first times 0.200. That's also to the first. I'm just putting the ones there to indicate that that the reaction is first order in hydrogen peroxide and first order in iodide. All right, now all we do is take this and divide it by 0.2 and then again by 0.2. And our K value equals 0.000460 divided by 0.2 0.0115. Rate has units of molarity over time. In this case, it's molarity over seconds. Molarity over seconds, molarity, molarity. So the units of K, molarity per second. On the right-hand side, we have molarity squared. Divide both sides by molarity. K will have units of molarity to the -1, seconds to the -1. So in other words, on the left side of the equal sign, this is units of molarity over time. On the right side, molarity times molarity, so molarity squared. Divide both sides by molarity squared, and we get 1 over molarity, 1 over seconds. I'm not going to be a stickler about the units of K, because for any rate law like this, where we have a second order reaction overall, this will be our unit. If it's third order, that'll change this. If it's first order, that'll change this. Right. Lastly, what do we do with these two concentrations, 0.3 and 0.4? So the rate, all we have to do is put rate is equal to, now we know K, 0.0115. Sorry. 0.0115. Our rate's going to be in molarity per second, 0.300. Again, I'm just putting that first power in there to indicate that to remind you that it's first order in each one. You don't really have to do that. And our rate is equal to times 0.3 times 0.4, 0.00138. Our units, molarity per second. All right. This is how we find the rate law by the method of initial rates. We know initial concentrations, we find the initial rate, or we're given the initial rate, and then we plug them into this equation, and we just did this empirically. Okay, let's look at this problem. A little, excuse me, a little out of line here. Not too bad though. So let's take a look at this. Can we find the rate law now that we have three reactants? We have three reactants. We have BrO3 minus. What's the name of this? What is this ion called? If ClO3 minus is chlorate, BrO3 minus is bromate. Bromate, bromide, and hydrogen ion. Okay, so let's take a look at the numbers. If we look at experiments 1 and 2, these two stay the same. Bromate doubles. If bromate doubles, what happens to the rate? Does the rate double? Does the rate quadruple? Does the rate decrease? We go from 8 times 10 to the minus 4 to 16 times 10 to the minus 4. So 0.0008, 0.0016. That's doubling. So we know that the exponent of the order of the reaction is 1 for bromate. As this doubles, the rate doubles. What about bromide? If we look at experiments 1, let's see. Let's look at experiments 2 and 3. If we look at experiments 2 and 3, bromate stays the same, bromide doubles, hydrogen ion stays the same. Stays the same, doubles. As this doubles, what happens to the rate? We go from 1.6 times 10 to the minus 3 to 3.2 times 10 to the minus 3. This doubles. Double the concentration, you double the rate. The exponent for bromide is 1. First order for bromate, first order for bromide. Now, what about hydrogen ion? Let's look at experiments 1 and 4. Bromate stays the same, bromide stays the same, hydrogen ion doubles. This goes from 8 times 10 to the minus 4th to 3.2 times 10 to the minus 3rd. The rate quadruples for hydrogen ion. So another way of saying it is that the rate for the hydrogen ion concentration, as we double this concentration, the rate quadruples. That means that this is a squared relationship. Think of it this way. If we increase this by a factor of 2, and this increases by a factor of 4, 2 squared will give us that 4. So this is how we just do this empirically. So the rate law for this particular reaction then is this. Rate is equal to K times bromate, per bromate, 3 bromide, and hydrogen ion concentration squared. So this reaction, according to the data that are shown here, first order, second order, the overall order of this reaction is fourth order. Now look at the overall reaction. Look at the overall reaction. Coefficient here is 1, coefficient here is 5, coefficient here is 6. These numbers, excuse me, it's first order in bromate, but it's only first order in bromide. This 5 does not matter. This 6 does not matter. Those are not the numbers for the orders of those components. Okay, last one. This, by the way, is on worksheet number 4. So for worksheet 4, take a look at that. Oh boy, this is off again. Okay. Now, let's see what's happening here. If we look at experiments 2 and 3, this stays the same. This doesn't exactly double, does it? This is not the same. And now we have rates that are a little bit different. So we have a different reaction, and we can't just look at it and say, oh, this is easy. Because, quite frankly, it's kind of the way life works. It's not always easy. It's not always straightforward. So here's how we're going to do this. This is the systematic way to approach it. Because we have 2 experiments where B does not change, I'm going to use these 2 experiments and we'll work with these numbers. Okay, so the rate law is equal to K times, this is A into B. All we know is that this is A to some number and B to some number. That's all we know. So here's what we do to solve it systematically. Let's just put the numbers into the rate law. So here, 1.620. This is equal to K. Don't know what K is. A is 0.80, B is 0.30. I hope you can see that. I hope it's not off the screen. Okay, you see what we just did here? All I did was take the data for a given experiment and I plugged all of the data into the rate law as we know. Now, because experiment 2 will give us the same concentration as B, I'll put those numbers in. Keep in mind these units here are molarity. Okay. I have a set of experimental data. This is experiment number 3. This is experiment number 2. I'm going to divide one by the other. So now we're just going to do a little bit of math here, a little bit of algebra. We have this number divided by this number, just flat raw numbers, and the units cancel out. So 1.62 divided by 1.013. 1.599, we'll call this 1. Since those are 4 sig figs, since these are each of 4 sig figs, I'll use 4 sig figs here. All right, now let's go to the right side of the equal sign. The K's, divide right up. These 2 are both to the M. And then these 2, same number raised to the same power, whatever that power is, those cancel right out. So my equation reduces to this. Another way of saying that is that this is 0.80 divided by 0.50 to the M. And 0.8 divided by 0.5 is 1.600. This raised to this power equals this. Since these two are virtually equal, m is 1. Okay, so that's pretty easy now to find the order. But it wasn't obvious. I couldn't just look at it and say, okay, this doubles, then this doubles. Now I actually have to put the data in and do the calculation. Now what I'd like you to do on the worksheet, do the exact same process here in order to find the exponent for B, the order of the reaction in terms of B. So now that we know the value of M is 1, pick 2 experiments and plug in the numbers. So here, let's set it up. It doesn't matter which ones you pick. It all works out the same. We can do 1 and 2 or 1 and 3. I'll just do 1 and 2 just because it sounds fun. 1.03 or 1.013 is equal to K times 0.50 to the first power times 0.30 to the n. Now, I'll put in data from experiment 1. 0.0150 is equal to K times. Now, this is 0.20 to the first power, and this is times 0.10 to the n. Do the exact same process that we did over there. These units cancel. On the left side of the reaction, we have a number. K cancels. It's the same reaction, same temperature, same K. Now, 0.5 divided by 0.2. Now we have a number that we can just put in here. And then we have 0.3 over n. So let's just take it one more step. And then you can do the final finishing. 1.013 divided by 0.015. 67.53. 67.5. This is equal to, what's 0.5 divided by 0.2? That's 5 halves. Sure, 2.50 times this divided by this. What is 0.3 divided by 0.1? So this is what we just did right over here. 0.3 divided by 0.1 is 3 to the n. Now, all you have to do is find n. All you have to do is find n. Okay, and I'll let you finish that off. You can determine n, and then you can write the rate law. Once we know the rate law, once we know the value of n and m, we can pick any data set, plug in rate, concentration, and solve for K. Excuse me. And that's it. Once we know K, then we can plug in any other set of data and calculate the rate from that. So the rate law is a very powerful tool for looking at rates of reaction. Okay, so here's the summary. What we've done so far in chapter 14. So you can pause this if you want. I'm going to move ahead. All right, now. The integrated first order rate law. So by now, by the way, you should be done with worksheet 4. Worksheet 4, this is moving into the topics for worksheet 5. So we know that rate is defined as change in concentration over change in time. This is a reactant, so the rate is decreasing, so we have the negative sign in front. And so if we take this out of it, rate is equal to K times reactant raised to the m power. If it's first order, m is 1. If it's first order, rate is 1. So we have this equation. Change in concentration over change in time is equal to K times concentration of A to the first power. This is the rate. This is how rate is defined. We're putting that definition of rate in the rate law. So if we arrange this, if we rearrange this, let's put T on the right and put A over here. This becomes negative delta A all over concentration of A, dividing both sides by concentration of A, is equal to K delta T. K times minus delta T. Okay. Now, since I moved the negative sign over to the right, let me get rid of this one. Now what I do is I'm going to integrate. No, let me write this in a little bit different form. So this is dA d concentration of A all over concentration of A is equal to minus K, where little d represents the delta. Now we integrate. And what we end up with is, when we integrate 1 over A, we end up getting natural log. So this is natural log of A at time t. We integrate between 0 and time t. Sometime that we start the experiment and sometime down the road. Natural log of A at time t minus natural log of A times 0 is equal to minus K T at times T minus KT at times 0. Well, if T is times 0, that whole second term just disappears. So we end up with this. So now what we do is combine all of this, natural log of A. Natural log of this minus natural log of this gives us this. So I'm going to erase this here. Natural log of this minus natural log of this gives us this relationship. This is how you combine logs. A at time t over A0 initially equals minus KT. So this is how we get the integrated first order rate law. You do not have to do this integration. For those of you who are in calculus, it's not a hard one to do, and makes sense. Like all equations, you don't have to memorize this, but here's what you do have to know. You have to know when to use it. In other words, it is first order. If it's first order, you're using a natural log relationship. Okay. Okay, I seem to be struggling with the screen today. Okay. So here's another way of writing that first order rate law, which quite frankly, we don't really care about at the moment. We'll just use the way it is in the other slide. This is a plot of concentration of A versus time. We've talked about this. You know how to get the rate at any point in the reaction from the slope of the line, from the slope of the line between the points you want or the slope of the tangent line. Concentration decreases if we plot instead natural log of A instead of A natural log of A, natural log of A versus time will give us a straight line. It will give us a linear relationship if the reaction is first order. And here are data that show that. And so this is just an illustration. So here's time and N2O5. Remember the N2O5 data that we talked about in class on Wednesday? We looked at the reaction. N2O5 goes to 2 of these, goes to 4 NO2s and oxygen. Excuse me. It turns out that the rate of this reaction, measured experimentally, which we can actually get from data, the rate is first order in N2O5. And how do we know that? We take time and concentration. We know that if we plot time and concentration, it goes like this. But if we take the log of this number, the natural log of this number, so in your calculator, plug this number in, you get this. Plug this number in, you get this. Now if we plot time on the x-axis and natural log of concentration on y, we get a straight line. Okay. So here's an example. Here we have some weird compound. This goes to nitrogen and C2H6. Here are our data. Time, concentration. We know how to plot it. We know how to find rate at any given point. Okay, so much for that. I don't know where I was going with that, but let's see. So let's do this. Is this, how do we know if this is first order? Let's look at this. Let's look at 100 to 150. We could go 0 to 100, 100 to 200. Let's do that. 0 to 100. Let's compare these numbers. The difference between these two numbers is 0.064. 100 seconds. The difference between, 100 seconds, this is the difference between the two concentrations. Now let's go from 100 to 200 to take the same amount of time. The change in concentration here is 0.22 to 0.170. So over here, the difference is 0.050. Not the same. The change is not the same. In other words, we have some curvature to this particular plot. Let's look at the difference between 200 and 300. The difference between 0.17 and 0.13, that is 0.038. Different yet. So now, let's take those 3 points, those same 3 points that were differences. Now let's take the 0.284, and let's take the natural log. This is minus 1.258, minus 1.26. .220 natural log minus 1.51. Uh, 0.193 natural log minus 1.65. I'm going to jump down to, no, let's do 1 point. What do I want to do? Don't really need this one, do I? Not for the same comparisons. Skip this one. 0.170 minus 1.77 and the bottom 1.132. Minus 2.02. All I did was take these numbers, take the natural log of them. All right, now, 0 to 100, what's our difference? What's our gap? 0.25. 0.025. Oh, 0.25. The difference between these two numbers is 0.25. The difference between these two numbers, 0.26. Why these two numbers? Because the gap is still 100 seconds. This 100-second gap from here to here, 0.25. In other words, as x changes consistently, y is changing consistently. So all we just did was figured out that this is how that we have a first order reaction, because log of concentration versus time is linear. Okay, now, there are a couple of other ways we can deal with the data. I'm going to work with, let's take a look at this problem. A first order reaction is 35% complete at the end of 55 minutes. What is the value of K? We're given time, we're given K, and we're given some proportion between original concentration and concentration at time t. So we'll use this. Now, I said you don't have to memorize it. I hope you do. You probably will by using it enough. Natural log A at time t over A0 equals minus KT. This is the integrated first order rate law, and this is why it is so useful. We're looking for K. We don't know what K is. Are we given time? Yes, we are, 55 minutes, so we know time. Do we know these two? No, but we know something about the ratio. Now let's take a look at it. So A is going to other things. We started with how much of this? We don't know how much, but whatever we started with was 100%. So let's call A0 100%. What is the concentration of A at 55 minutes? What is the concentration of A at time t? The reaction is 35% complete. What does it mean if the reaction is 35% complete? Well, of the 100% we started with, how much has gone to the right? Well, that's the 35%. 35% is what's gone to the right. So what are we left with at time t? 65%. We've lost almost a third of it. But we've lost a little over a third of it that's gone to the right. So all we have to do, this is a ratio. All we have to do is put in the numbers 65% to 100%. 35% complete means that 35% of the original amount of A is reacted. And we're left with 65%. 55 minutes. So now we just plug in the numbers and solve for K. That's all there is to it. So natural log 65 over 100, units divided out, equals minus K times 55 minutes. So for those of you keeping score at home, let's do 65 divided by 100. And let's take the natural log. Minus 4.31 minus K times 55 minutes. Divide both sides by 55. 0.00783. And this is going to be minutes to the minus 1. Is equal to K. Nope, let's see. And we change the sign. We change the sign, so that's a positive. Okay, so let's see. This is one way to use the first order rate law. Let me just come back to this equation for a moment. The value in the integrated first order rate law if we know the rate constant, remember this is the rate constant that's used in the rate law, okay? There are four things here. An original concentration, a concentration at some point down the road, the rate constant, and the time. This is the time it takes for this to decrease to that. Okay, I'm going to talk about half-life. I think many of you already have an idea of what half-life is. Half-life is how long does it take to lose half your stuff? How long does it take to lose half of what you started with? So if we're starting here, well, let's say that this is time. Time 0, we start with 1. At some time interval, 1 minute, we're left with that. How long does it take to lose half of that? Well, maybe 2 minutes. At 3 minutes, we have half of what we had there. So as we plot the data, this is actually a first order loss. And these are the equations for half-life. So if we started with 2, we end with 1. In other words, the ratio of A times T to A we started with is 1 to 2. If we start with 100%, half-life means we have 50% left. Natural log of 1/2, 50 over 100, is equal to minus KT. If we take this, rearrange it, natural log of this is minus 0.693. We divide both sides. Once we get that minus 0.693, divide by minus K. T 1/2 is the half-life. This is the time it takes to lose half of what you started with. Okay. Okay, let's do this. For a first order reaction, A goes to products. We know that if for its first order, the exponent for A is 1. The order of the reaction for A is 1. So the original concentration, if this is 0.5 molar, if this is 5 molar, the half-life is 25 minutes, let's calculate K. Now, how do we calculate K? 0.693 all over K. We're given the half-life, 25 minutes. Geez, it gets me every time. 25 minutes. Okay, multiply both sides by K, divide both sides by 25 minutes, and we get .0277. So we can round this to 0.0. Since we have 2 sig figs here, we should probably round that to 0.028. Now keep in mind that our units are minutes to the minus 1. Next step, write the rate law for this reaction. Well, we always start rate equals K. We have A. Do we know the order? Sure, it's first order. This is the rate law. Calculate A at T equals 525 minutes. Calculate A at 525 minutes. Okay. Now we use the integrated first order rate law. Natural log of A at time T. That is what we don't know. This is A at some time down the road. The original concentration that we started with is 5.0 molar. Since these are in a ratio, of course, the unit here will be molarity, is equal to minus, what's K? I just had it, 0.028. Units to the minus 1 times 525. Okay, and so our right side of the equation here is 14.6. Tell you what, I'm just going to keep the numbers and round at the end. So now what do we do? Well, this is equal to natural log of a at time t minus natural log of 5.0 is equal to 16.4. There's another way to do this. There's another way to do this. I think it might be a little easier to do it now. So I'm going to do it now. 16.4. And I'm running out of time, so I'm going to end with this. Natural log. So if we have x, natural log of x, natural log and e to the x are inverse functions. Let me back up. So let me use a number like 100. The log of 100. Well, 100 is equal to 10 squared. Log is base 10 log. So the log of 10 to the second is equal to 2. The log of 10 to the second is 2. Now, 10 to the x is the opposite function. 10 to the x and log of x are inverse functions. They undo each other. So 10 to the x, in other words, 10 to the second is equal to 100. So in other words, if I take the log of 100, I get 2. If I take 10 to the second, that's equal to 100. They're inverse functions. So in other words, 10 to the log of x is equal to x. And the log of 10 to the x is equal to x. So the same thing is true with the e function. E to the x and natural log of x undo each other. So e to the natural log of x is equal to x. So what I'm going to do is simply take e to both sides. So a times t, 5.0 molar, is equal to 16 e to the 16.4. And let's see, 16.4. And e to the x is, okay, it's a big number. 1.33 times 10 to the 7. 1.33 times 10 to the 7. Actually, you know what? I have to shut this down. I'm going to stop here. I'm going to finish this next time. All right, so let me stop the Zoom. Let's see. Here we go. And we'll pick up for the lecture on Monday with this.